Hi, my name is Nicole Vanelli. I'm going to be a rising senior at Salve Regina University, where I major in environmental studies, and I also have biology and political science minors. And I was lucky enough to do my Ernest F. Hollings Scholarship internship at the Great Bay National Estuarine Research Reserve in Greenland, New Hampshire. My mentors for this internship were Christopher Peter, the research coordinator here, and Anna Lomine, the Margaret A. Davidson Fellow here at Great Bay. And I studied if eelgrass can help offset nitrogen pollution in Great Bay. So just a quick outline, I'm going to give you an overview of things I worked on besides this eelgrass study, and then just go over some background for my research, and then dive into the research and think about where it could possibly go next. So first, some context on Great Bay. Great Bay is located in the seacoast region of New Hampshire. Waters from Great Bay flow into the Piscataqua River and out to the Gulf of Maine. And so while Great Bay technically entails Little Bay as well, this research solely focuses on Great Bay and its three rivers, the Lamprey, the Squamscott, and the Winnicott. And then a quick overview of my internship in general. So quick introductions of the people that made this internship possible. Christopher Peter, the research coordinator here, Anna Loween, my co-mentor, and Heather Ballestero, our biological technician. These three people are just so smart, and just listening to them talk about science and life has been quite the privilege this summer, and I really enhanced my internship experience. Special shout out to Anna, who defended her thesis last week and somehow still took me on as an intern and has taught me so much this summer. That is just really hard to do, and it's amazing. And so now some things I got to work on besides just my eelgrass research. So some long-term monitoring of the salt marsh, where I helped measure salinity of pore water wells throughout the marsh to see if climate change and saltwater intrusion is affecting the marsh over time. So this is also on the Great Bay waterfront. And then this is me using a refractometer to measure salinity. And sometimes we had to cross some pretty treacherous lands to get to the pore water wells, which was my favorite part, just getting my boots and my hands dirty and being able to find the wells and all of the chaos of a marsh. I got to help out with our NEARS tea time study, where we buried tea bags in the marsh to measure decomposition rates in low marsh versus high marsh over time. And I just helped bury them, pick where we're going to bury them, and identify the vegetation around that, which was really fun and really cool. I helped Chris out with his environmental DNA research, which we call eDNA. So it basically just tells us what is living in Great Bay and what subtidal habitats they utilize. Our education program held day camps to teach local children about Great Bay and all of its creatures. And this is something I got to help out with every now and then that I really enjoyed. So on the left is me teaching them about the low tide. So I took this picture of them all exploring all the critters that hang out in the mud flat. And I got to help out with the osprey program as well. So I'm helping this kid build an osprey kite. And speaking of osprey, the coolest moment of my entire life, I got to hold a juvenile osprey when she turned 4 weeks, and we banded her. And it was so amazing. And she did drool some fish guts on me, but it was absolutely worth it. I helped out with a restoration project we called turf tying. So we tied eelgrass to these things called turfs with dissolvable ties, so that when you place the turfs in Great Bay, there's hopes that they'll root and then reproduce and come back to a place in Great Bay where they haven't thrived in a few years. And just in general, I just got to enjoy how beautiful Great Bay is, and being out on the water was my absolute favorite part of the internship. So on the left, I'm learning how to snorkel and just taking in how breathtaking eelgrass beds can be. And on the right, I took this picture when they were just looking for one of our light loggers, just because it was just so beautiful to be able to enjoy the blue sky and the current and the Footman Islands in the background here. And I just love being able to swim and enjoy my coworkers' company and the beauty of Great Bay. So my question is, does Zostera marina, or eelgrass, contribute to nitrogen removal in Great Bay? So is eelgrass somehow removing nitrogen from the water column differently than an unvegetated site would? So that makes it important for us to discuss the ecosystem services of eelgrass first before we dive into this research. So eelgrass provides a feeding area for fish, invertebrates, and waterfowl. And it also provides a nursery for finfish and shellfish. And it's really cool when you're just in the water and being able to see all of the snails and sponges and animals that just use Great Bay, the eelgrass beds in Great Bay as a habitat, and it just shows how important eelgrass is to Great Bay. It produces great quantities of oxygen for all these organisms. It combats ocean acidification by utilizing CO2. It helps hold sediment in place with its roots, thus preventing coastal erosion. It helps filter sediments in the water, so it captures these suspended solids, which then improves water quality. And it also filters nitrogen from the water column, which is the most important part of this research, and sequesters carbon. So it removes nutrients from the water column by either uptaking nitrogen or being involved in its removal. But however, eelgrass in the last decade or so has taken a pretty big hit in Great Bay. So while eelgrass does uptake nitrogen, too much nitrogen can cause eutrophication, which causes algal blooms that block light from eelgrass and actually kills it off. And it also depletes the water depletes oxygen from the water. So between 1996 and 2014, according to Burdick et al. 2020, in Great Bay, there's been a 44% loss of acreage and a 79% loss of biomass. So as you can see, using ArcGIS, I created a visual so you can see how astronomical that really is. So that brings us to nitrogen loads in Great Bay. So how much nitrogen is killing eelgrass? According to Burdick et al. 2020, estuaries with greater than 50 kilograms of nitrogen per hectare per year show significant eelgrass decline. So in 2006, before some wastewater treatment facility upgrades and in a rather rainy year, so just more runoff, Great Bay showed to have 267 kilograms per hectare per year of nitrogen, which is astronomically over that 50 kilogram threshold. But then 10 years later, after significant upgrades to these wastewater treatment plants and on rather low rain years, there was less storm runoff, we still had a whopping 116 kilograms of nitrogen per hectare per year, which is still more than double that threshold. So nitrogen loading is still a problem in Great Bay. But where is this nitrogen coming from? So like we touched upon, it's coming from wastewater treatment facilities is one source, a point source. So all of those dots, the circles on the map show us a wastewater treatment facility, and there's 17 that contribute nitrogen to Great Bay, 4 of which are in Maine. And then there's also non-point sources. So there's leakage from septic tanks, there's storm runoff, which is just worsened by civilization and developing communities with paved surfaces. And there's atmospheric deposition as well. So while Great Bay looks pretty small, its watershed is rather large. So there's a lot of communities that are contributing nitrogen to Great Bay. So what happens when this nitrogen is deposited into the water column? So when wastewater treatment facilities or non-point sources run into Great Bay, they come in the form of dissolved inorganic nitrogen and dissolved inorganic nitrogen, and that together creates a pool of total dissolved nitrogen in the water column. However, dissolved inorganic nitrogen is the most important part of this study because that's how eelgrass can take up nitrogen, is in that form. So I have ammonium and nitrate here to visualize that. And so there's 3 types of removal the eelgrass can take part in. There's short-term removal, where it uptakes it through its roots or through its leaves in the water column and utilizes it for biological processes like photosynthesis. And then there's long-term nitrogen removal, where it gets buried in the sediments. And as previously stated, seagrass roots help keep that sediment in place. And so that nitrogen doesn't get kicked up for a long time and it stays under there for a while. And then there's permanent removal, which is denitrification. And denitrification is the reduction of nitrate into nitrite and ultimately into N2 gas that is released back into the atmosphere. And seagrass creates an environment with favorable conditions to promote this denitrification. And this is permanent removal because once it is N2 gas is deposited back into the atmosphere, it is not a usable form that the estuary can use because of those triple bonds that make it really difficult for seagrasses to utilize. And so now into some methods of the research. So eelgrass sites were selected randomly based on their requirements that they should be at least 15 meters from any bed edge and have a minimum percent cover of 50%. And then they had each eelgrass site was paired with an unvegetated mudflat site as a control. So as you can see, I circled all the eelgrass sites in Great Bay green and the mudflat sites we used red. And now some sampling methods. So we went on the boat to each site monthly to collect a variety of samples. And while my subset of data focused mostly on the water column, those 60 mils of filtered water that I had bolded. We collected so much more. So I just want to go through everything that we're able to sample. So we sampled those 60 mils of filtered water from the water column that I used for total dissolved nitrogen and dissolved inorganic nitrogen. And then we collected samples for chlorophyll A, total suspended solids, gas samples to test for greenhouse gases in the water, MIMS to test for N2 in the water, and sediment cores, which was my specialty sampling because sometimes with the strong current and the high tide, it was difficult to get down to the sediment in order to get a syringe of 6 centimeters full of sediments. But I somehow mastered it, and you would see my feet fly up in the air for a concerningly long time, and then I would come back up with a syringe full of sediment. So that was something that I really enjoyed, and that kind of made everybody laugh. And now the water quality lab. So the UNH water quality analysis lab was a huge part of my internship experience, as I come from a pretty small school that doesn't have access to the kind of instruments that UNH does. And it was so overwhelming at first, but I learned so much. So as I focus on nitrogen removal in the water column, I bolded those first 3 parameters because that's what I used in my results section in my research. So I learned to run the machines to get those values. So ammonium and nitrate were measured using automated calorimetry. Total dissolved nitrogen was measured via high temperature catalytic oxidation. But I also learned how to do so much more that I spent a lot of time in the lab doing. So I just want to touch on that. I also learned how to prep and run a combustion machine to get particulate nitrogen and carbon values. So on the right is actually me folding total suspended filters that we're going to teeny tiny little pieces that will run into the combustion machine to get these particulate values. I learned how to use a gas chromatograph to test for greenhouse gases in gas samples. And I learned how to do a hot ethanol extraction of chlorophyll A, and then use a spectrophotometer to get absorbances. So I learned a lot in the lab. And now for some results. So for total dissolved nitrogen, I wanted to run total dissolved nitrogen in milligrams of nitrogen per liter versus habitat to see which habitat just has more nitrogen. And so a pooled t-test indicates a significant difference of total dissolved nitrogen between eelgrass beds and mudflat. So as you can see there, I have a significant p-value that's less than 0.05 that indicates that there is more dissolved nitrogen in general in the mudflat sites. But then that got me thinking, total dissolved nitrogen is important and it is exciting and it is significant. However, that dissolved inorganic nitrogen pool of that dissolved total nitrogen is what eelgrass is able to remove. So I ended up adding our ammonium, our nitrite, and our nitrate values together to get a dissolved inorganic nitrogen pool so that we could see if there was a significant difference between dissolved inorganic nitrogen and habitat. So I ran another full t-test and with these values, and we see that even more significant number of 0.024 as my p-value. And as you can see, the mudflat site had almost double the mean of the eelgrass site. So eelgrass has to be removing nitrogen from dissolved inorganic nitrogen from the water column in order for this to happen. And this is really exciting because that leads us to so many things. So just in summary, there is lower dissolved inorganic nitrogen in eelgrass beds versus an unvegetated mudflat bed, indicating that eelgrass is removing nitrogen from Great Bay to some extent. So what does that mean for the future? So this research can go in so many different ways, but one way that it could go on is quantifying nitrogen removal processes. So how much nitrogen is being removed due to denitrification? How much is being buried in the sediments? How much is eelgrass uptaking? And you can actually even measure growth rates and apply that to uptake numbers. So there's a lot of ways you can measure that nitrogen just rather than general removal. And then it's important for restoration efforts to know what eelgrass is doing and how it removes nitrogen from the water column. And of course, with any science comes a policy and management aspect. So regulating nitrogen from wastewater treatment facilities, but also using eelgrass as a tool to figure out what's that happy medium where there's enough nitrogen where eelgrass isn't being killed, but it's also helping remove it. So we have to find that balance because eelgrass can actually be used as a positive feedback mechanism because when you plant eelgrass, it improves water quality, which promotes the growth of more eelgrass. And I think that eelgrass could be really used as a tool to save wastewater treatment facilities a lot of money in filtering naturally, but we have to find that balance. So I think that's really where the research would go next in order to then apply that to policy. So just some quick acknowledgements of my scholarship. of my internship in general. So the NOAA Ernest F. Hollings undergraduate scholarship program that funded this whole internship and all my research. Chris Peter and Anna Lewine for being the best mentors ever, and Chris Kincaid for being my NOAA mentor, and the entire Gimner staff for really welcoming me and trying to expose me to as many things as possible. And I also would like to thank the UNH Water Quality Lab and Jackson Lab for learning to be a part of so many different things and use all the instruments and really gain that experience, because that was so valuable to me. And here are some references I used throughout, some literature that I used throughout my presentation. And that's pretty much it. So thank you for listening. And Great Bay is an amazing place, and I've had such an amazing experience, and I would love to see where this eelgrass research can go next. Thank you.